this video, we are going to be continuing talking about reactions that can be performed on hydrocarbons. But now we are going to be focusing on alkenes and alkynes. As a review, I just want to remind you that alkene molecules are going to be hydrocarbons that contain one or more double bonds, while alkyne molecules are going to be molecules that contain one or more triple bonds. Understand that these functional groups that are part of the hydrocarbon family are very reactive. So we can be adding hydrogen atoms across that carbon-carbon double bond or triple bond, or we can be adding hydrogen and hydroxyl groups. Now, that is possible because these carbon-carbon double bonds or carbon-carbon triple bonds are easily broken, and they can be providing electrons to form new bonds. So the two addition reactions that we are going to be exploring in chapter 11 are called, first, the hydrogenation reaction, which means that we are going to be adding hydrogen, to each of the carbons that are held together by a carbon-carbon double bond or triple bond. And then the other reaction is going to be hydration, which means that there's a carbon atom that is going to receive an H, and another carbon atom is going to receive an OH. As you can see, both of these reactions are going to need catalysts, and as we explored previously, a catalyst is going to be a molecule that speeds up the reaction, and understand that that is their whole job. They are going to be produced at the end of the reaction so they can continue and process the reactions. In a hydrogenation reaction, as a product, we can obtain an alkane, while when we have a hydration reaction, we are going to be obtaining as a product an alcohol. Hydrogenation reactions are more common than what you may think. Understand that these hydrogenation reactions have been used in the food industry to produce products like shortening, and even margarine. So what is happening there is that they are taking these molecules that are carboxylic acids that have an alkene motif, and they're going to be turning them into an alkane motif. And I'm going to put that in parentheses because all we're doing is adding hydrogen, to each of the carbons that were held by the double bond. So in this case, each of these carbons used to have, let me just put the word alkene below. They were attached only to one hydrogen atom, and as you can see, now they have two each. So we went from one hydrogen atom to two hydrogen atoms. That's where these two hydrogens were incorporated in the molecule. And we're going to learn about this reaction further when we discuss lipids in the biochemistry section of this course. So when it comes to the hydrogenation reaction, as you can see, we are going to be adding hydrogen atoms to the carbon-carbon double bond or the triple bond. Remember, in this process, we can use catalysts that can be platinum, nickel, or palladium. So any of the three can be used. And remember that they are just going to be speeding up the reactions. They are not going to be involved directly or being added to the product. So if we start with an alkene, and that alkene undergoes the hydrogenation reaction, we are going to form an alkane. Because as I mentioned before, if I highlight the atoms, each carbon that is part of the carbon-carbon double bond in this hydrogenation reaction, basically we are going to erase the carbon-carbon double bond, and in its place we are going to create a brand new bond to hydrogen. And those hydrogens come from the H2 molecule that we're reacting the reactant with. When it comes to alkynes, understand that in alkyne we have a carbon-carbon triple bond. So in essence, when we write the product of the reaction, we need to erase two of the bonds, because when the hydrogenation of alkynes produce, we are going to be adding 4 hydrogen atoms. As you can see in the alkane product that we produce, each carbon that used to be in the carbon-carbon double bond, each carbon gets 2 hydrogen atoms. That's where the 4 hydrogen atoms go. Now we are going to be dealing with a hydration reaction. In a hydration reaction, again, you know that it is hydration because we're going to have water and acid added to the system. Again, your acid is your catalyst. Now, in a hydration reaction, the functional group that it is produced is always an alcohol. Now, when it comes to this, you need to understand that those hydrogen atoms and that hydroxy atom are not added randomly. Okay? What happens is that the hydrogen atom from water, okay, is going to form a bond with the carbon atom in the carbon-carbon double bond with the most hydrogen atoms. And that means that is directly attached to it. And we're going to see that in the examples once we practice predicting the products of the reactions. So remember, the hydrogen atom is going to go to the carbon that is directly attached to the most hydrogen atoms. When it comes to the hydroxyl group, the hydroxyl group from water is going to form a bond with the second carbon atom in the double bond, meaning the bond that has the fewest hydrogen atoms directly attached to it. So let's say that I give you an example of this addition, and I'm just going to do this on the side, because what you guys can see is that in the example that I have on the slides, this molecule of ethene, when we're adding the hydrogen and the OH, it doesn't matter which carbon atom gets the hydrogen in the OH, because this molecule specifically, if we cut it in the middle, has symmetry, meaning the right side of the molecule looks like the left side of the molecule. So let me give you an example in which this rule of the carbon that has the most hydrogens will get the hydrogen and the carbon that has the least hydrogens get the OH will apply. Let's say that we are going to do the hydration reaction, and RxN is my shorthand for reaction, in which we have the following alkene. And again, to write it as a whole, This is going to be reacting with water and acid. Okay. Understand, before I continue, that H2SO4 implies H plus because sulfuric acid is a strong acid, meaning it is a source of H plus. So let's say that we have the following alkene and we are going to react it under hydration conditions. First, we need to notice what are going to be the carbon atoms that are attached through the double bond. As you can see, we have the carbon atom on the left and the carbon atom on the right. Now, the carbon atom that it is on the left side is bonded to a hydrogen directly and is bonded to this carbon. Remember that CH3, those three hydrogens are bonded to the carbon, not directly bonded to the carbon that I highlighted in purple. The carbon on the right is directly bonded to this carbon and is directly bonded to that carbon. So what this means is that the carbon that is highlighted in purple contains one hydrogen directly attached to it, while the carbon that is on the right side from that double bond is not directly attached to any hydrogen. So what does this mean? That when we have to write the product of this reaction, it's going to be CH3, C is going to be bonded to H. Now, because in a hydration reaction and also in a hydrogenation reaction, we're going to break the double bond. Now we're going to write the substituents that were present in the atoms across that carbon-carbon double bond, where we're not going to write the double bond. Now we're going to write the atoms that are going to be adding across what used to be double bonded. I'm going to highlight the carbons in the same color that we had before. And again, because the purple, or the one that is on the left, contains directly or is directly attached to hydrogen, is going to receive the incoming hydrogen. The carbon that is highlighted in orange, because it doesn't have hydrogen directly attached to it, that is going to be receiving the hydroxyl group. And those, remember, are going to come from the water. We can visualize water as H and OH. Let's practice now giving a list of reactions. What are going to be the products formed from the reagents given? So now we're going to be practicing these based on part K in our worksheet. So I'm going to be writing the names of each of the reactions first, and then I'm going to be writing the structures of the products. So the first reaction, we're going to have an alkane reacting with oxygen, and when that happens, that's going to be a combustion reaction. In a combustion reaction, the product of the reaction is always going to be CO2, water, and energy. And understand that when it comes to this, I don't expect you guys to balance the chemical reaction. Just know that the product of the reaction for a combustion of an alkane is CO2, water, and energy. Reaction number 2 and reaction number 3, as you can see, I'm just going to highlight the reagents in yellow, contain H2 and a catalyst. In the case of Roman numeral 2, we have palladium. In Roman numeral 3, we have hydrogen, and we have as a catalyst platinum. Remember that PD, palladium, or that PT, platinum, are not going to be added to any atom in our reactant. They are just there to speed up the reaction. Both of these reactions are going to be hydrogenation reactions. And in this hydrogenation reaction, we are going to be adding hydrogen to each carbon that is bonded by a carbon-carbon double bond. So how do we predict the product of this reaction? We are going to rewrite the molecule as given, but we are not going to include the carbon-carbon double bond. We are only going to include a single bond. So we're going to write a CH3 bonded to a carbon, which is bonded to another CH3. Now is going to be single bonded to an H. That CH is bonded to a CH2 molecule, and that CH2 molecule is bonded to a CH3 molecule. Because this is a hydrogenation reaction, each carbon that used to be bonded by the double bond is now going to receive a hydrogen. It's hard to see the yellow, so I'm going to use a black pen. But if I highlight the atoms, I think it will work better. The carbon-carbon double bond, which used to exist here, now those atoms are going to have now each of them a hydrogen. On Roman numeral 3, if we need to predict the product of the reaction, again, we are going to rewrite the molecule as is. With its substituents, the only thing that we're not going to include is that second bond in the double bond. If I highlight the atoms that used to be part of the double bond, okay, now each of them is going to be receiving a hydrogen. Now let's move on to Roman numeral 4, 5, and 6. Each one of these reactions is going to be hydration reaction. In these hydration reactions, the reason why I know it's a hydration reaction is because we are reacting acid and water. That is going to be our other reactant. And we have those paired with alkenes. Okay? Then in a hydration reaction, remember, we have to think of water as a molecule that is going to donate an H and is going to donate an OH. Okay? So when we are dealing with number 4, we are going to now, I'm going to be highlighting the carbon-carbon double bond. If I number these carbons as carbon 1 and carbon 2, understand that the carbon atom, or you can do A and B. It doesn't matter the labeling, okay? Let me just change it to A and B so there's no confusion. So carbon A and carbon B, understand that carbon A is directly attached to one hydrogen. Carbon B is directly attached to 2 carbon atoms. So that means that carbon A is going to receive the incoming hydrogen and carbon B is going to receive the incoming hydroxyl group. So when we write the product of the reaction, in reaction 4 is going to be CH3 bonded to CH, which now is going to receive a hydrogen. Then the carbon atom that is bonded to is going to receive the OH. Then this is bonded to a CH group, bonded to a CH3 group, and then the carbon that now has the OH was bonded to a CH3. Let's deal with the reaction on number 5. Number 5 is going to be very similar to the example that is written, not that I wrote, but the one that it is illustrated in the slide. Meaning, that if we move to the previous slide is going to be like the example of ethene, where we are going to be having a molecule that has symmetry. Meaning that if I take this alkene and I cut it and I fold it through here, the left side and the right side are going to reflect each other. In those cases, when we perform a hydration reaction, remember, we are going to be producing one product. And that single product is going to be one in which again, we're going to write the molecule that we started with. The only thing that we are not going to be including is the carbon, the second bond in the carbon-carbon double bond. And in this case, one carbon is going to get the H, one carbon is going to get the OH. If you forget about this and then you write, oh no, this is going to produce another product. One in which, now this carbon has the H and this carbon is going to have the OH. Understand that these two are going to be the same molecule. That's why overall we form one product. And that only happens with alkenes that have symmetry. The last case, so this is, let me just make a note. This is a symmetrical alkene with same number of hydrogens in carbon-carbon double bond. So, what about if we have a molecule in which the carbon-carbon double bond is directly attached to the same number of hydrogens, but now the molecule is not symmetrical? So how about if we have an unsymmetrical alkene with the same number of hydrogens in the carbon-carbon double bond. Remember, directly attached to any of the carbons in the carbon-carbon double bond. When that happens, we will form two products. Because what happens is that when the addition happens, we are going to have, so if I label these carbons as carbon A and as carbon B, since they have the same number of hydrogens directly attached to it, when the reagents come to do the addition, they are going to give, in one instance, the H to the carbon A and the OH to carbon B. And then they're going to do the vice versa reaction, which means that we're going to be giving an H to carbon B and the OH to carbon A. Remember, that is only possible if we have an unsymmetrical alkene in which the carbon-carbon double bond is directly attached to the same number of hydrogens. So now I'm going to write the products of that reaction. So the first product is going to be CH3 bonded to CH, that is also bonded to a CH3. That CH is bonded to another CH, which is bonded to another CH, and that CH is bonded to a CH2, which is bonded to a CH3. So these are the carbons that were attached to each other through double bond. Now, in this instance, this is going to receive the H, this is going to receive the OH. Then the second product of the reaction will be when we have CH3 bonded to CH, bonded to CH3, that is bonded to CH, is bonded to another CH, which is bonded to a CH2, which is bonded to a CH3. And in the next instance, that carbon that used to be double bonded, now the first one is going to have the OH, while the next one is going to have the H.